We are drifting in a great ocean of space and time. In that ocean, the events that shape the future are working themselves out. Each creature and every world, to the remotest star, owe their existence to the great, coursing, implacable forces of nature, but also to minor happenstance. We are carried with our planet around the sun. The Earth has made more than 4 billion circuits of our star since its origin. The sun itself travels about the core of the Milky Way galaxy. Our galaxy is moving among the other galaxies. We have always been space travelers. These fine sand grains are all more or less uniform in size. They've been produced from bigger rocks through ages of jostling and rubbing, abrasion and erosion, driven in part by the distant moon and sun. So the roots of the present lie buried in the past. We are also travelers in time. But trapped on Earth, we've had little to say about where we're going in time and space, or how fast. But now, we're thinking about true journeys in time and real voyages to the distant stars. A handful of sand contains about 10,000 grains, more than the total number of stars we can see with the naked eye on a clear night. But the number of stars we can see is only the tiniest fraction of the number of stars that are. What we see at night is the merest smattering of the nearest stars, with a few more distant bright stars thrown in for good measure. Meanwhile, the cosmos is rich beyond measure. The total number of stars in the universe is larger than all the grains of sand on all the beaches of the planet Earth. Long ago, before we had figured out that the stars are distant suns, they seemed to us to make pictures in the sky. Just follow the dots. The constellation called the Big Dipper today in North America has had many other incarnations. Every culture, ancient and modern, has placed its totems and concerns among the stars, from a Chinese bureaucrat to a German wagon. But very ancient cultures would have seen different constellations, because the stars move with respect to one another. We can give a computer the present three-dimensional positions and motions of the nearby stars, and then run the patterns back into time. Every constellation is a single frame in a cosmic movie, but because our lives are so short, because the star patterns change so slowly, we tend not to notice it's a movie. 1 million years ago, there was no Big Dipper. Our ancestors, looking up and wondering about the stars, saw some other pattern in the northern skies. We can also run a constellation, Leo the Lion say, forward in time and see what the patterns in the stars will be in the future. 1 million years from now, Leo might be renamed the constellation of the radio telescope, although I suspect that radio telescopes then will be as obsolete as stone spears are now. Or here's the constellation of Cetus, the whale. A million years ago, it may have been called something else, perhaps the spear. Now let's run fast forward through 1 billion nights. Millions of years from now, some other, very different image will be featured in this cosmic movie. In Orion, the hunter, things are changing not only because the stars are moving, but also because the stars are evolving. Many of Orion's stars are hot, young, and short-lived. They're born, live, and die within a span of only a few million years. If we run Orion forward in time, we see the births and explosive deaths of dozens of stars flashing on and winking off like fireflies in the night. If we wait long enough, we see the constellations change. But if we go far enough, we also see the star patterns alter. The two-dimensional constellations are only the appearance of stars strewn through three dimensions. Some are dim and near, others are bright but farther away. Could a space traveler actually see the patterns of the constellations change? For that, you must travel roughly as far as the constellation is from us. Here, we're traveling hundreds of light years, circling all the way around the stars of the Big Dipper. The inhabitants of planets around other stars will see very different constellations than we do, because their vantage points are different. Here we are in the constellation Andromeda, or at least a model of it, next to the constellation Perseus. Andromeda, in the Greek myth, was the maiden who was saved by Perseus from a sea monster. This star just above me is Beta Andromedae, the second brightest star in the constellation, 75 light years from the Earth. The light by which we see this star has spent 75 years traversing interstellar space on its journey to the Earth. In the unlikely event that Beta Andromedae blew itself up a week ago Tuesday, we will not know of it for another 75 years, as this interesting information, traveling at the speed of light, crosses the enormous interstellar distances. When the light we see from this star set out on its long interstellar voyage, the young Albert Einstein, working as a Swiss patent clerk, had just published his epical special theory of relativity here on Earth. We see that space and time are intertwined. We cannot look out into space without looking back into time. The speed of light is very fast, but space is very empty, and the stars are very far apart. In fact, the distances that we've been talking about up to now are very small by the usual astronomical standards. In fact, the distance from the Earth to the center of the Milky Way galaxy is 30,000 light years. From our galaxy to the nearest spiral galaxy like our own, called M31, and which is also within, that means behind, the constellation Andromeda, is 2 million light years. When the light we see today from M31 left on its journey for Earth, there were no human beings on the Earth, although our ancestors were nicely evolving and very rapidly to our present form. There are much greater distances in astronomy. The distance from the Earth to the most distant quasars is 8 or 10 billion light years. We see them as they were before the Earth itself accumulated, before the Milky Way galaxy was formed. The fastest space vehicles ever launched by the human species are the Voyager spacecraft. They are traveling so fast that it's only 10,000 times slower than the speed of light. The Voyager spacecraft will take 40,000 years to go the distance to the nearest stars, and they're not even headed towards the nearest stars. But is there a method by which we could travel in a conveniently short time to the stars? Can we travel close to the speed of light? And what's magic about the speed of light? Can't we travel faster than that? It turns out that there is something very strange about the speed of light, something that provides the key to our understanding of time and space. The story of its discovery takes us to Tuscany in northern Italy. There's something almost timeless about this place. A century ago, it probably looked very much the same. If you had traveled these roads in the summer of 1895, you might have come upon a 16-year-old German high school dropout. His teacher had told him that he would never amount to anything, that his attitude destroyed classroom discipline, that he'd be better off out of school. So he left and came here, where he enjoyed wandering these roads and giving his mind free rein to explore. One day, he began to think about light, about how fast it travels. In our everyday life, we always measure the speed of a moving object relative to something else. I'm moving at about 10 kilometers an hour relative to the ground. But the ground isn't at rest. The Earth is turning at more than 1,600 kilometers an hour. The Earth itself is in orbit around the Sun. The Sun is moving among the drifting stars, and so on. It was hard for the young man to imagine some absolute standard to measure all these relative motions against. He knew that sound waves are a vibration of the air, and their speed is measured relative to the air itself. But sunlight travels across the vacuum of empty space. Do light waves move relative to something else? And if so, he wondered, relative to what?
That teenage dropout's name was Albert Einstein, and his ruminations changed the world. He had been fascinated by Bernstein's 1869 People's Book of Natural Science. Here, on its very first page, it describes the astonishing speed of electricity through wires and light through space. Einstein wondered, perhaps for the first time here in northern Italy, what the world would look like if you could travel on a wave of light. To travel at the speed of light. What an engaging and magical thought for a teenage boy on the road where the countryside is dappled and rippling in sunlight. You couldn't tell you were on a light wave if you were traveling with it. If you started on a wave crest, you would stay on the crest and lose all notion of it being a wave. Something funny happens at the speed of light. The more Einstein thought about such questions, the more troubling they became. Paradoxes seemed to pop up all over if you could travel at the speed of light. Certain ideas had been accepted as true without sufficiently careful thought.
One of those ideas had to do with the light from a moving object. The images by which we see the world are made of light and are carried at the speed of light, 300,000 kilometers a second. You might think that the image of me should be moving out ahead of me at the speed of light plus the speed of the bicycle. If I'm moving towards you faster than a horse and cart, then my image should be approaching you exactly that much faster. My image ought to arrive earlier. But in reality, you don't see any time delay. In a near collision, for example, you always see everything happen at once. Horse, cart, swerve, bicycle, all simultaneous. But how would it look if it were proper to add the velocities? Since I'm heading towards you, you'd add my speed to the speed of light. So my image ought to arrive before the image of the horse and cart. I'd be cycling towards you quite normally, To me, a collision would suddenly seem imminent. But you'd see me swerve for no apparent reason and have a collision with nothing. Now, the horse and cart aren't headed towards you. Their image would arrive only at the speed of light. Could it seem to me that I just missed colliding while to you it wasn't even close? In precise laboratory experiments, scientists have never observed any such thing.
If the world is to be understood, if we are to avoid logical paradoxes when traveling at high speeds, then there are certain rules which must be obeyed. Einstein called these rules the special theory of relativity. Light from a moving object travels at the same speed no matter whether the object is at rest or in motion. Thou shalt not add my speed to the speed of light. Also, no material object can travel at or beyond the speed of light. There's nothing in physics that prevents you from traveling as close to the speed of light as you like. 99.9% the speed of light is just fine. But no matter how hard you try, you can never gain that last decimal point. For the world to be logically consistent, there must be a cosmic speed limit.
The crack of a whip is due to its tip moving faster than the speed of sound. It makes a shock wave, a small sonic boom in the Italian countryside. A thunderclap has a similar origin. So does the sound of a supersonic airplane. So why is the speed of light a barrier, any more than the speed of sound? The answer is not just that light travels about 1,000,000 times faster than sound. It's not merely an engineering problem like the supersonic airplane. Instead, the light barrier is a fundamental law of nature, as basic as gravity. Einstein found his absolute framework for the world, this sturdy pillar among all the relative motions of the cosmos. Light travels just as fast no matter how its source is moving. The speed of light is constant relative to everything else. Nothing can ever catch up with light.
Einstein's prohibition against traveling faster than light seems to clash with our common sense notions. But why should we expect our common sense notions to have any reliability in a matter of this sort? Why should our experience at 10 kilometers an hour constrain the laws of nature at 300,000 kilometers a second? Relativity sets limits on what humans ultimately can do. The universe is not required to be in perfect harmony with human ambition. Imagine a place where the speed of light isn't its true value of 300,000 kilometers a second, but something a lot less. Let's say 40 kilometers an hour, and strictly enforced.
Just as in the real world, we can never reach the speed of light. The commandment here is still, thou shalt not travel faster than light. But we can do thought experiments on what happens near the speed of light. Here, 40 kilometers an hour, the speed of a motor scooter. You can't break the laws of nature. There are no penalties for doing so. The real world, and this one, are merely so arranged that transgressions can't happen. The job of physics is to find out what those laws are. Before Einstein, physicists thought that there were privileged frames of reference, some special places and times against which everything else had to be measured. Einstein encountered a similar notion in human affairs, the idea that the customs of a particular nation, his native Germany or Italy or anywhere, are the standard against which all other societies must be measured. But Einstein rejected the strident nationalism of his time. He believed every culture had its own validity. And also in physics, he understood that there are no privileged frames of reference. Every observer, in any place, time, or motion, must deduce the same laws of nature.
Caldo.
A speed is simply how much space you cover in a given time. As any kid on a motor scooter knows, Since near the velocity of light, we cannot simply add speeds. The familiar notions of absolute space and absolute time, independent of your relative motion, must give way. That's why, as Einstein showed, funny things have to happen close to the speed of light. There, our conventional perspectives of space and time strangely change.
Your nose is just a little closer to me than your ears. Light reflected off your nose reaches me just an instant in time before your ears. But suppose I had a magic camera so that I could see your nose and your ears at precisely the same instant.
With such a camera, you could take some pretty interesting pictures. Paolo says goodbye to his little brother Vincenzo.
Ciao, Vincenzo. Ciao,
And rides off. He's now going more than half the speed of light. He's almost catching up with his own light waves. This compresses the light waves in front of him, and his image becomes blue. The shorter wavelength is what makes blue light waves blue. Also, Paolo becomes skinny in the direction of motion. This isn't just some optical illusion. It really happens when you travel near the speed of light. As he roars away, he leaves his own light waves stretched out behind him. Long light waves are red. We say that his receding image is red-shifted. Now, Paolo leaves for a short tour of the countryside. He experiences something even stranger. Everything he can see is squeezed into a moving window just ahead of him. Blue shifted at the center, red shifted at the edges. To a passerby, Paolo appears blue shifted when approaching, red shifted when receding. But to him, the entire world is both coming and going at nearly the speed of light. Roadside houses and trees that he's already gone past still appear to him at the edge of his forward field of view, but distorted and red shifted. When he slows down, everything again looks normal. Only very close to the speed of light does the visible world get squeezed into a kind of tunnel. You would really see these distortions if you could travel near the speed of light. Someday, perhaps, interstellar navigators will take their bearings on stars behind them, whose images have all crowded together on the forward view screen. The most bizarre aspect of traveling near the speed of light is that time slows down. All clocks, mechanical and biological, tick more slowly near the speed of light. But stationary clocks tick at their usual rate. If we travel close to light speed, we age more slowly than those we left behind. Paolo's watch and his internal sense of time show that he's been gone from his friends for only a few minutes. But from their point of view, he has been away for many decades. His friends have grown up, moved on, and died. And his younger brother has been patiently waiting for him all this time. The two brothers experience the paradox of time dilation. They've encountered Einstein's special relativity.
Vincenzo.
This was just a thought experiment, but atomic particles traveling near the speed of light do decay more slowly than stationary particles. As strange and counterintuitive as it seems, time dilation is a law of nature.
Traveling close to the speed of light is a kind of elixir of life. Because time slows down close to the speed of light, special relativity provides us with a means of going to the stars. This region of northern Italy is not only the cauldron of some of the thinking of the young Albert Einstein, it is also the home of another great genius who lived 400 years earlier, Leonardo da Vinci. Leonardo delighted in climbing these hills and viewing the ground from a great height as if he were soaring like a bird. He drew the first aerial views of landscapes, villages, fortifications. I've been talking about Einstein in and around this town of Vinci, in which Leonardo grew up. Einstein greatly respected Leonardo, and their spirits, in some sense, inhabit this countryside still. Among Leonardo's many accomplishments in painting, sculpture, architecture, natural history, anatomy, geology, civil and military engineering, he had a great passion. He wished to construct a machine which would fly. He made sketches of such machines, built miniature models, constructed great full-scale prototypes. And not a one of them ever worked. Mainly because there were no machines of adequate capacity available in his time. The technology was just not ready. The designs, however, were brilliant. For example, this bird-like machine here in the Leonardo Museum in the town of Vinci. Leonardo's great designs encouraged engineers in later epochs, although Leonardo himself was very depressed at these failures. But it's not his fault. He was trapped in the 15th century. A somewhat similar case occurred in 1939, when a group of engineers calling themselves the British Interplanetary Society decided to design a ship which would carry people to the moon. Now, it was by no means the same design as the Apollo ship, which actually took people to the moon some years later. But that design suggested that a mission to the moon might one day be a practical engineering possibility. Today, we have preliminary designs of ships which will take people to the stars. They are constructed in Earth orbit, and from there, they venture on their great interstellar journeys. One of them is called Project Orion. It utilizes nuclear weapons, hydrogen bombs, against an inertial plate, each explosion providing a kind of putt-putt, a vast nuclear motorboat in space. Orion seems entirely practical and was under serious development in the United States until the signing of the international treaty forbidding nuclear weapons explosions in space. Personally, the Orion starship is the best use of nuclear weapons I can think of, provided the ships don't depart from very near the Earth. Project Daedalus is a recent design of the British Interplanetary Society. It assumes the existence of a nuclear fusion reactor, something much safer as well as more efficient than the existing nuclear fission power plants. We do not yet have fusion reactors. One day, quite soon, we may. Orion and Daedalus might go 10% the speed of light. So a trip to Alpha Centauri, 4.5 light years away, would take 45 years, less than a human lifetime. Such ships could not travel close enough to the speed of light for the time-slowing effects of special relativity to become important. It does not seem likely that such ships would be built before the middle of the 21st century, although we could build an Orion starship now. For voyages beyond the nearest stars, something must be added. Perhaps they could be used as multi-generation ships. So those arriving would be the remote descendants of those who had originally set out centuries before. Or perhaps some safe means of human hibernation might be found, so that the space travelers might be frozen and then thawed out when they arrive at the destination centuries later. But fast interstellar spaceflight, approaching the speed of light, is much more difficult. That's an objective not for 100 years, but for 1,000 or for 10,000. But it also is possible. A kind of interstellar ramjet has been proposed, which scoops up the hydrogen atoms which float between the stars, accelerates them into an engine, and spits them out the back. But in deep space, there is one atom for every 10 cubic centimeters of space. For the ramjet to work, it has to have a frontal scoop hundreds of kilometers across. When the ship reaches relativistic velocities, the hydrogen atoms will be moving, with respect to the interstellar spaceship, at close to the speed of light. If precautions aren't taken, the passengers will be fried by these induced cosmic rays. There's a proposed solution. A laser is used to strip electrons off the atoms and make them electrically charged while they're still some distance away. And an extremely strong magnetic field is used to deflect the charged atoms into the scoop and away from the rest of the spacecraft. This is engineering on a scale so far unprecedented on the Earth. We are talking of engines the size of small worlds. Suppose that the spacecraft is designed to accelerate at 1g, so we'd be comfortable aboard it. We'd be going closer and closer to the speed of light until the midpoint of the journey. Then the spacecraft is turned around and we decelerate at 1g to the destination. For most of the trip, the velocity would be very close to the speed of light and time would slow down enormously. By how much? Barnard's star could be reached by such a ship in 8 years ship time. The center of the Milky Way galaxy in 21 years. The Andromeda galaxy in 28 years. Of course, the people left behind on the Earth would see things somewhat differently. Instead of 21 years to the center of the galaxy, they would measure it as 30,000 years. When we got back, very few of our friends would be around to greet us. In principle, such a journey, mounting the decimal points closer and closer to the speed of light, would even permit us to circumnavigate the known universe in 56 years ship time. We would return tens of billions of years in the far future, with the Earth a charred cinder and the sun dead. Relativistic spaceflight makes the universe accessible to advanced civilizations, but only to those who go on the journey, not to those who stay home. These designs are probably further from the actual interstellar spacecraft of the future than Leonardo's models are from the supersonic transports of the present. But if we do not destroy ourselves, I believe that we will one day venture to the stars. When our solar system is all explored, the planets of other stars will beckon.
Space travel and time travel are connected. To travel fast into space is to travel fast into the future.
We travel into the future, although slowly, all the time. But what about the past? Could we journey into yesterday? Many physicists think that this is fundamentally impossible, that there is no way we could build a device which would carry us backwards into time. Some say that even if we were to build such a device, it wouldn't do us much good, that we couldn't significantly affect the past. For example, suppose you traveled into the past and somehow or other prevented your own parents from meeting. Why, then you would probably never have been born, which is something of a contradiction, isn't it, since you're clearly there. Other people think that the two alternative histories have equal validity, that they're parallel threads, skeins of time, that they could exist side by side. The history in which you were never born and the history that you know all about. Perhaps time itself has many potential dimensions, despite the fact that we are condemned to experience only one of those dimensions. Now, suppose you could go back into the past and really change it by, let's say something like persuading Queen Isabella not to bankroll Christopher Columbus. Then you would have set into motion a different sequence of historical events, which those people you left behind you in our time would never get to know about. If that kind of time travel were possible, then every imaginable sequence of alternative history might in some sense really exist. Would it be possible for a time traveler to change the course of history in a major way? Well, let's think about that.
History consists, for the most part, of a complex multitude of deeply interwoven threads, biological, economic, and social forces that are not so easily unraveled. The ancient Greeks imagined the course of human events to be a kind of tapestry created by three goddesses, the Fates. Random minor events generally have no long-range consequences, but some, which occur at critical junctures, may alter the weave of history. There may be cases where profound changes can be made by relatively trivial adjustments. The further in the past such an event is, the more powerful its influence. What if our time traveler had persuaded Queen Isabella that Columbus's geography was wrong? Almost certainly some other European would have sailed west to the New World soon after. There were many inducements: the lure of the spice trade, improvements in navigation, competition among rival European powers. The discovery of America around 1500 was inevitable. Of course, then there wouldn't be any postage stamps showing Columbus, and the Republic of Colombia would have some other name. But the big picture would have turned out more or less the same.
In order to affect the future profoundly, a time traveler would have to pick and choose. He'd probably have to intervene in a number of events which are very carefully selected, so he could change the weave of history. It's a lovely fantasy to explore those other worlds that never were.
If you had H.G. Wells's time machine, maybe you could understand how history really works. If an apparently pivotal person had never lived, Paul the Apostle or Peter the Great or Pythagoras, how different would the world really be?
What if the scientific tradition of the ancient Ionian Greeks had prospered and flourished? It would have required many social factors of the time to have been different, including the common feeling that slavery was right and natural. But what if that light that had dawned on the Eastern Mediterranean some 2,500 years ago had not flickered out? What if the scientific method and experiment had been vigorously pursued 2,000 years before the Industrial Revolution, our Industrial Revolution? What if the power of this new mode of thought, the scientific method, had been generally appreciated? I think we might have saved 10 or 20 centuries. Perhaps the contributions that Leonardo made would have been made 1,000 years earlier, and the contributions of Einstein 500 years ago. Not that it would have been those people who would have made those contributions, because they live only in our timeline. If the Ionians had won, we might by now, I think, be going to the stars. We might at this moment have the first survey ships returning with astonishing results from Alpha Centauri and Barnard Star, Sirius and Tau Ceti. There would now be great fleets of interstellar transports being constructed in Earth orbit, small unmanned survey ships, liners for immigrants, perhaps, great trading ships to ply the spaces between the stars. On all these ships, there would be symbols and inscriptions on the sides. The inscriptions, if we look closely, would be written in Greek. The symbol, perhaps, would be the dodecahedron, and the inscription on the sides of the ships to the stars, something like Starship Theodorus of the planet Earth.
If you were a really ambitious time traveler, you might not dally with human history or even pause to examine the evolution of life on Earth. Instead, you would journey back to witness the origin of our solar system from the gas and dust between the stars. 5 billion years ago, an interstellar cloud was collapsing to form our solar system. Most clumps of matter gravitated towards the center and were destined to form the sun. Smaller peripheral clumps would become the planets. Long ago, there was a kind of natural selection among the worlds. Those on highly elliptical orbits tended to collide and be destroyed, but planets in circular orbits tended to survive. But if events had been only a little different, the Earth would never have formed, and some other planet at some other distance from the sun would be around. We owe the existence of our world to random collisions in a long-vanished cloud. Soon, the central mass became very hot. Thermonuclear reactions were initiated, and the sun turned on, flooding the solar system with light. But the growing smaller lumps would never achieve such high temperatures and would never generate thermonuclear reactions. They would become the Earth and the other planets, heated not from within, but mainly by the distant sun. The accretion continued until almost all the gas and dust and small worldlets were swept up by the surviving planets. Our time traveler would witness the collisions that made the worlds. Except for the comets and asteroids, the chaos of the early solar system was reduced to a remarkable simplicity. 9 or so principal planets in almost circular orbits and a few dozen moons. Now, let's take a different look. If we view the solar system edge on and move the sun off screen to the left, we see that the small terrestrial planets, the ones about as massive as the Earth, tend to be close to the sun. The big Jupiter-like planets tend to be much further from the sun. But is that the way it has to be? Computer studies suggest that there may be many similar systems about other stars, with the terrestrials in close and the Jovian planets further away. But some systems might have Jovians and terrestrials mixed together. There may be great worlds like Jupiter looming in other skies. Rarely, the Jovian planets may form close to the star, the terrestrials trailing away towards interstellar space. Our familiar arrangement of planets is only one, perhaps typical, case in the vast expanse of systems. Often, one fledgling planet accumulates so much gas and dust that thermonuclear reactions do occur. It becomes a second sun. A binary star system is formed. For most of these worlds, the vistas will be dazzling. Not a one of them will be identical to the Earth. A few will be hospitable. Many will appear hostile. Where there are two suns in the sky, every object will cast two shadows. What wonders are waiting for us on the planets of the nearby stars? Are there radically different kinds of worlds, unimaginably exotic forms of life? Perhaps in another century or two, when our solar system is all explored, we will also have put our own planet in order. Then we will set sail for the stars and the beckoning worlds around them. In that day, our machines and our descendants, approaching the speed of light, will skim the light years, leaping ahead through time, seeking new worlds. Einstein has shown us that it's possible. We will journey simultaneously to distant planets and to the far future. Some worlds, like this one, will look out onto a vast gaseous nebula, the remains of a star that once was and is no longer. In all those skies, rich and distant and exotic constellations, there may be a faint yellow star, perhaps barely visible to the naked eye, perhaps seen only through the telescope. The home star of a fleet of interstellar transports exploring this tiny region of the great Milky Way galaxy. The themes of space and time are intertwined. Worlds and stars, like people, are born, live, and die. The lifetime of a human being is measured in decades, but the lifetime of the sun is 100 million times longer. Matter is much older than life. Billions of years before the sun and Earth even formed, atoms were being synthesized in the insides of hot stars and then returned to space when the stars blew themselves up. Newly formed planets were made of this stellar debris. The Earth and every living thing are made of star stuff. But how slowly, in our human perspective, life evolved from the molecules of the early oceans to the first bacteria. The reason evolution is not immediately obvious to everybody is because it moves so slowly and takes so long. How can creatures who live for only 70 years detect events that take 70 million years to unfold, or 4 billion? By the time one-celled animals had evolved, the history of life on Earth was half over. Not very far along to us, you might think, but by now, almost all the basic chemistry of life had been established. Forget our human time perspective. From the point of view of a star, evolution was weaving intricate new patterns from the star stuff on the planet Earth, and very rapidly. Most evolutionary lines became extinct. Many lines became stagnant. If things had gone a little differently, a small change of climate, say, or a new mutation, or the accidental death of a different, humble organism, the entire future history of life might have been very different. Perhaps the line to an intelligent, technological species would have passed through worms. Perhaps the present masters of the planet would have had ancestors who were tunicates. We might not have evolved. Someone else, someone very different, would be here now in our stead, maybe pondering their origins. But that's not what happened. There was a particular sequence of environmental accidents and random mutations in the hereditary material. One particular timeline for life on Earth in this universe. As a result, the dominant organisms on the planet today come from fish. Along the way, many more species became extinct than now exist. If history had a slightly different weave, some of those extinct organisms might have survived and prospered. But occasionally, a creature thought to have become extinct hundreds of millions of years ago turns out to be alive and well. The coelacanth, for example. For 3.5 billion years, life had lived exclusively in the water. But now, in a great breathtaking adventure, it took to the land. But if things had gone a little differently, the dominant species might still be in the ocean, or they might have developed spaceships to carry them off the planet altogether. From our ancestors, the reptiles, there developed many successful lines, including the dinosaurs. Some were fast, dexterous, and intelligent. A visitor from another world or time might have thought them the wave of the future. But after nearly 200 million years, they were suddenly all wiped out. Perhaps it was a great meteorite colliding with the Earth, spewing debris into the air, blotting out the sun and killing the plants that the dinosaurs ate. I wonder when they first sensed that something was wrong. The successors of the dinosaurs came from the same reptilian stock, but they were able to survive the catastrophe that destroyed their cousins. Again, there were many branches which became extinct. And again, had events been only a little different, those branches might have led to the dominant form today. For 40 million years, a visitor would not have been much impressed by these timid little creatures, but they led to all the familiar mammals of today. And that includes the primates. About 20 million years ago, a space-time traveler might have recognized these guys as promising. Bright, quick, agile, sociable, curious. Their ancestors were once atoms made in stars. Then simple molecules, single cells, polyps stuck to the ocean floor, fish, amphibians, reptiles, shrews. But then they came down from the trees and stood upright. They grew an enormous brain. They developed culture, invented tools, domesticated fire. They discovered language and writing. They developed agriculture. They built cities and forged metal. And ultimately, they set out for the stars, from which they had come 5 billion years earlier. We are star stuff, which has taken its destiny into its own hands. The loom of time and space works the most astonishing transformations of matter. Our own planet is only a tiny part of the vast cosmic tapestry, a starry fabric of worlds yet untold. Those worlds in space are as countless as all the grains of sand on all the beaches of the Earth. Each of those worlds is as real as ours. In every one of them, there's a succession of incidents, events, occurrences, which influence its future. Countless worlds, numberless moments, an immensity of space and time. And our small planet, at this moment, here we face a critical branch point in history. What we do with our world right now will propagate down through the centuries and powerfully affect the destiny of our descendants. It is well within our power to destroy our civilization and perhaps our species as well, if we capitulate to superstition or greed or stupidity.
We can plunge our world into a darkness deeper than the time between the collapse of classical civilization and the Italian Renaissance. But we are also capable of using our compassion and our intelligence, our technology and our wealth to make an abundant and meaningful life for every inhabitant of this planet, to enhance enormously our understanding of the universe and to carry us to the stars.
In our motorbike sequence, we showed how the landscape might look if we were barreling through it at close to the speed of light. Since then, inspired by this sequence, Ping Kang Seung at Carnegie Mellon University produced an exact computer animation. This is what you'd see if you were traveling at ordinary speeds through this red and white lattice. But this is how it would appear if you were traveling the same route at close to the speed of light. We're probably many centuries away from traveling close to the speed of light and experiencing time dilation. But even then, it might not be fast enough if we wanted to travel to some distant place in the galaxy, say, and then come back to Earth in our own epoch. Some years after completing Cosmos, I found myself taking time out from my scientific work to write a novel about travel to the center of the Milky Way galaxy. I was willing to imagine beings and civilizations far more advanced than we, but I wasn't willing to ignore the laws of physics. Was there, even in principle, a way to get very quickly to 30,000 light years from Earth? So I put this question to my friend Kip Thorne of the California Institute of Technology. He's a leading expert on the nature of space and time. Kip thought about it for a while and then answered with about 50 lines of equations, which showed that a really advanced civilization might establish and hold open wormholes, which we might think of as tubes through the fourth dimension, which connect the Earth with another place in the universe without having to traverse the intervening distance, something like crawling through a wormhole in an apple. I was very happy with this result, and I used it as a key plot device in Contact. But such wormholes through space would also be time machines, it seemed to me. And I used that notion in my novel Contact as well. Kip Thorne and his colleagues later proved, or so it seemed, that time travel of this sort was possible. Here, look at this. The key question being explored now is whether such time travel can be done consistently, with causes preceding effects, say, rather than following them. Does nature contrive it so that even with a time machine, you can intervene to prevent your own conception, for example? Even if time travel of this sort is really possible, it's far in our technological future. But maybe other beings, much more advanced than we, are voyaging to the far future and the remote past, not a measly 40 years ago on Earth, but to witness the death of the sun, say, or the origin of the cosmos.